Hello everyone, my name is Xinyu Zhang. I will be presenting our paper titled Text CRS, a Generalized Certified Robustness Framework Against Textual Adversarial Attacks, co-authored with Hanbin Hong, Yuan Hong, Peng Huang, Binghui Wang, Zhongjie Ba, and Kui Ren. Deep learning models are vulnerable to adversarial attacks, as illustrated below. Introducing noise or a perturbation to an image can deceive a model into misclassification. A parrot, for example, could be wrongly identified as a turkey simply because of the noise. To date, adversarial attacks have been met with corresponding empirical defenses. However, these measures are only effective against certain adversarial attacks and fail in the face of adaptive attacks. A promising solution in this ongoing arms race against unseen or adaptive attacks is providing provable robustness for the model. We aim to develop algorithms that are certifiable robust, ensuring the model's predictions remain stable within a defined range of adversarial perturbations. As shown here, certified defense guarantees accurate classification of an image as a parrot when the perturbation radius p-norm is less than 10/2055. Among various procedures for certified defense, randomized smoothing stands out. It imposes no limitations on the model's architecture and maintains satisfactory accuracy on large-scale dataset. Our work focuses on text and language models. Notably, language models are vulnerable to adversarial perturbations, as seen in the following illustrations. In a standard text classification process, inputting a text to a sentiment classification model yields an sentiment label, say negative. On the contrary, in an adversarial concept, slight alterations to the text can fool the same model into outputting a positive sentiment. Our key concern is with four typical textual adversarial attacks: synonym substitution, word reordering, word insertion, and word deletion. To counter such adversarial attacks, our work aspires to enhance the robustness of language models. Previous defenses, such as adversarial training, feature detection, input transformation, are only effective against specific adversarial attacks and can be broken by adaptive attacks. One promising way to win the arms race against unseen or adaptive attacks is to provide certified robustness guarantees for the model. We proposed Text CRS. Its goal is to develop certifiable robust algorithms, ensuring stable model predictions against a range of adversarial perturbations. Its technique employs randomized smoothing that is model agnostic and achieving acceptable accuracy for a large-scale dataset. Our Text CRS is the first generalized certified robustness framework against common word-level textual adversarial attacks through randomized smoothing. It certifies the robustness in the word embedding space without imposing restrictions on model architectures and demonstrates high universality and accuracy compared to state-of-the-art methods. Existing certified defenses cannot provide robustness guarantees against word-level operations due to the following three challenges. First, different data space. Words are unstructured strings, and there is no numerical relationship among discrete words. This makes it challenging to measure the L1 and L2 distance between words, as well as the perturbation distance between the original and adversarial text. Second, wide variety of operations. Previous work for images provide robustness guarantees against semantic transformations in image domain, such as rotation and scaling. However, they cannot be directly applied to the NLP domain because texts and words have a more heterogeneous discrete domain, and word insertion and deletion are new semantic transformations not involved in the image domain. Third, significant absolute attack distance stemming from the potential alteration of each word, as opposed to most pixels in image adversarial examples remaining unchanged. We propose 3 solutions to address the above challenges of applying certified robustness to language models. First, for different data space challenge, we first introduce the embedding layer in certified robustness in the field of NLP to map unstructured text into a numerical word vector space. Second, for wide variety of operations challenge, we systematically modeled a variety of adversarial transformations, constructing customized noise distribution for AI model robustness training, addressing the high heterogeneity of texture transformations. Third, for huge absolute attack distance, by innovating the certified robustness theory under various noise models, we expand the defense range of attacks, overcoming the huge textual adversarial distance. We proceed to describe our framework overview. We disentangle the general textual adversarial attacks into 2 operations within the embedding space: permutation U and embedding transformation W. We randomize this operation to achieving certified robustness. The diagram below shows the partition of input space into permutation space and embedding space, characterizing each operation as a mix of permutation and embedding transformation. Analyzing the characteristics of each operation, we select an appropriate smoothing distribution to ensure certified robustness for each of them. Upon constructing the framework, we craft novel certified robustness theorem for text classification. The basic AI models often exhibit uneven classification boundaries, and our text CRS first utilize robust training to smooth these boundaries. Then, we perform robust verification to evaluate the attack distance of the adversarial example that the model can defend. Specifically, robust training entails splitting the word vector space into permutation and embedding spaces. The training process incorporates noises that design for word position, permutation, and changing word embedding vectors. In terms of robust verification, we evaluate the attack distance that the model can defend based on 4 new certified robust theorems. This slide illuminates the theoretical guarantees our paper proposed. Under this framework, for each textual adversarial attack, we formulate unique theorems to guarantee their robustness. First, staircase randomization. Second, uniform-based permutation. Third, Gaussian-based embedding insertion. And the last one, Bernoulli-based embedding deletion. To further improve the certified accuracy, we develop a toolkit with 3 methods for the 3 steps in the training. First, optimized Gaussian noise. We analyze the embedding vectors of all words and observe that each element in the embedding vectors approximates a Gaussian distribution with a non-zero mean. So we can enhance the certified accuracy by modifying the Gaussian noise of each dimension. Second, embedding space reconstruction. To mitigate the disturbance of the embedding space, we introduce an encoder-decoder architecture to reconstruct the clean embedding space. The encoder-decoder can also be viewed as sanitizing the adaptive noise. This method can effectively improve accuracy in small dimension embedding space. Third, pre-trained large model. Fine-tuning from a pre-trained model is a typical training approach for large models. When applying high-level Gaussian noise to a large model, we can fine-tune it on a pre-trained large model trained with small Gaussian noise. Moving forward, I present the performance of text CRS versus previous methods. The following table details these comparative results. For synonym substitution, our text CRS outperforms safer for all noise levels under 3 datasets and 2 models. Text CRS is the first to provide certified robustness for word reordering, insertion, and deletion. Compared to clean vanilla, text CRS sacrifices only a small fraction of accuracy. Here is the experimental results for substitution and reordering. In left figures, a radius of 20 for a sentence with a length of 50 implies that each word can be substituted with its 4 closed-set synonyms in the source. In right figure, the radius 100 indicates that the text CRS certifies a text in which the sum of all word positions changes is less than 100. This slide shows the results for word insertion. The radius in the left figure denotes the cumulative embedding L2 distances between the original and the inserted word. In the right figure, the BERT model can withstand 53% and 11% of random word insertions among the top 5 and top 50 closed-set embeddings, respectively. Here is the results for word deletion attack. A radius 2 indicates that up to 2 words can be deleted while ensuring the certified robustness of the text. In essence, our framework is the first generalizable defender against common word-level textual adversarial attacks. We have disentangled general textual adversarial attacks into operations across permutation and embedding space. Via our introduced toolkit, we have improved certified accuracy against adversarial attacks in language models. Our code and further resources are accessible at the GitHub. Should any inquiries arise, please feel free to contact me via email. Thank you for your time and the platform to share our work.